All right, so energy. Energy was a big unit. We had a lot of stuff in energy, so I'm going to start by writing all the formulas out for us. All right, there were a ton of formulas in energy. The first and foremost of which, if I can find a good marker, there we go. The first of which was that the law of conservation of momentum, which states energy initial equals energy final. That was a big formula. Then there were all these ways to calculate your energy, such as gravitational potential energy equals mgh, kinetic energy equals 1/2 mv squared, spring potential energy equals 1/2 kx squared, and then there was work and power. So work was equal to force times displacement, and the displacement had to be in the same direction as the force. They had to be parallel to one another. Also, power was equal to force times velocity, or work divided by time, or change in energy divided by time. Work was also equal to the change in energy. So like if you had a change in energy, that was the work done on the object. I believe that sums up the formulas for energy. There was a lot of them. Keep in mind that energy, just like anything else, has like specific problems. So there are specific problems associated with this. I'll give you a couple just to make sure that y'all remember them. One of the most common ones that'll throw people off is the power one, where you have to figure out the force that you're lifting times the velocity that you're lifting it. So for instance, if we're lifting a elevator that's a 700 kilogram elevator, and we're going to lift it up at 5 meters per second, if you want to know the power rating, you would first have to find the force. Force would be 7,000 times 5. And if you're lifting a 700 kilogram elevator at 5 meters per second, you would have to be using 35,000 watts of power. So it's like force times velocity. That's usually how it comes into play. Another example is when you've done work. All right, so work being done. So we have like a slope here, and there's a box that's say 5 kilograms, and it's stationary right now, not moving, and it's at the bottom of the ramp. Okay, so it's at the bottom of the ramp. The energy here is equal to 0. And then what I'm going to do is I'm going to push it up here, and now it is 2 meters vertically off the ground, and it's going 5 meters per second. So I want to know the work done. Well, work is equal to the change in energy. So work would be equal to energy final minus energy initial. But we established that the energy initial is equal to what? 0. So the energy final is what I'm going to look for. What kinds of energy does this thing have at the end? Kinetic energy and gravitational potential. So you would have to do 1/2 mv squared plus mgh, and you'd be able to figure out what the work done was. So the work in this case, just to finish it up, would be 1/2 times 5 times, 1/2 times 5 times 5 squared plus 5 times 10 times 2. So you would get, the work would be 62.5 plus 100, or 162.5. And the unit for work is a, who's filming? Joules. All right. So work is equal to a joule, or 162.5 joules. All right. So that's one type of problem. All right. Another type of problem would be if, like, to see what cancels out. So a lot of times mass will cancel. So for instance, let's say that you are going to, like, somebody's going to dive off a diving board, right? And it's a 10-meter high diving board, all right? Or a diving platform, we'll say. So it's 10 meters high, and someone's going to dive off of it. This is my drawing of someone diving. Woohoo, he's diving. Got his hands pointed down. All right, so he's diving off of it, and I want to know how fast he's going 5 meters down. So 5 meters down, I want to know I want to know how fast he's going. Alright? What does his speed be? Alright, so what do you think I would do? What's my relationship? What formula am I starting with? Okay, I would need to know GP, that's true. But more importantly, what's the foundation for this? What am I using to figure out this information? Starts with a C, rhymes with a conservation. Okay, conservation of energy. You're using conservation of energy. So you need to know that the energy the guy has initially is equal to the energy the guy has finally. Okay? So you'll notice that I didn't give you the mass. But the mass is needed to calculate any of these formulas. So what's up with that? They're going to end up canceling each other out. So what type of energy does he have initially? Gravitational potential energy. And finally he has here and some GP. So kinetic energy final, gravitational potential final, and gravitational potential energy initial. So we've got mgh1 equals 1/2 mvf squared plus mgh2. Alright, so what happens to the m's? Look at them. They're in every term, so I can bam, bam, bam. And I'm left with 10 times 10 equals 1/2 times vf squared plus 10 times 5. How did I know he was 5 meters off the ground? Because he's 5 meters from the top, which would also be 5 meters from the ground. So you would end up with this formula, and you would get 50 equals 1/2 vf squared, or 10 meters per second equals vf. Alright, so that's an example of what we did with energy. Does anybody have any questions about that? Any concerns? You good? Straight? Good to know. Alright. Stop.